Hello guys, and welcome back to my channel Civil Construction and Tutor. In this video we'll discuss about the design of an strap footing. So here we have a question: design a strap footing for an eccentric footing and an internal footing subjected to a load PA 331 kN and PB 520 kN respectively, and the eccentric footing is subjected to column A of dimension 300 mm by 300 mm and internal footing to column B 300 by 300 mm. The column A footing is flush to the property line. The center to center distance between the column A and B is 3.51 meter. Take soil bearing pressure as 150 kN per meter square. Use M20 concrete and Fe 500 steel. So this is the diagrammatic representation of the question. Before that, let us go with the given. So for column A we have the service load as 331 kN. Then the design load will be 1.5 times of the service load, which is 497 kN. So this is the width of the column A and this is the depth of the column A. Similarly for column B, service load is 520 kN, design load will be 779 kN, width of column B 0.3 and depth of column B 0.3 meter. Similarly, characteristic strength of the concrete is 20 Newton per mm square for M20 concrete. Similarly, yield strength of the steel is 500 Newton per mm square considering Fe 500. Similarly, center to center distance between the column is 3.51 meter and soil bearing capacity is 150 kN per meter square. And the center to center distance, as the question has given us, LCC, that is 3.51 meter, and PAPB being the load individual for A and B respectively. LA is the length of the footing and LB is the length of the footing. So the very first step is to determine the length and width of the footing, and assuming 10% of the footing self weight, then the total load acting on the footing will be 1.1 times of the service load from the column. So 1.1 PA plus PB, this comes as 936 kN. Then the area required for footing is P total, that is the total load divided by soil bearing capacity. It is 150, so this comes as 6.24 meter square. Now in this strap footing we have to assume the width of the footing, and then we will go to the design of the length, or we will design the length of the footing. And as the property line is already fixed, that is it is flush to the property line, so we can directly go with the assumption of the width of the footing and adopt width of the footing BF as 1.5 meter. Then we know area is equal to LF into BF, you can see BF, and this will be equal for both to ensure that there is a uniform pressure distribution. So the width of the footing will be equal for both of them. Now we know area is equal to LF into BF. Now area is 6.24 and LF is nothing but LA plus LB. Okay, this is the area of foundation, not the beam. It doesn't include the beam, it only includes this two footings. So LF is equal to LA plus LB, and this LA plus LB is equal to 4.16 meter. Now using the same concept of this combined footing, considering slab only, now we know that for uniform soil pressure, the center of gravity of the footing and the resultant of the external load should coincide. That is, the CG of the footing and CG of the external load should lie at the same point, and for which and due to which the soil pressure will be uniform on the base. And for ensuring that the CG will be equal, let us find out this. Considering CG at distance x bar from the center of the column A, then moment about this point PA into x bar should be equal to PB into 3.51 minus x bar. The moment about CG should be equal to the load considered. So PA into x bar is equal to PB into 3.51 minus x bar, which is this much distance. I am representing this as y bar. So PA into x bar, we are getting this point. Now substitute the value of P and PB, will get x bar as 2.14 meter. So this distance is 2.14 meter. And similarly, center of gravity from the center of the column B, which will be equal to y bar, is equal to 3.51 minus x bar, which is 2.14. So this comes as 1.36 distance y bar. So just now we said that the CG of the footing and external load coincide. Now we'll use the center of gravity considering the area of the footing. So it is nothing but y bar is equal to A1 into lever arm plus A2 into lever arm divided by area required, that is A1 plus A2. So this is the center of gravity and we are considering y bar, that means this distance, that is center of gravity from the center of the column B. Now y bar is equal to A1 into area 1 LCC. So LCC means the center to center distance of the column A and column B plus LA. If there was any projection for the column A as well, then we have to add that also, but for now it is 0, we will not consider this. LA plus BA by 2. BA by 2 is nothing but this, we have this distance. Now we have to use this as well. So we come to this point considering LCC plus BA by 2. So we come at the edge minus LA by 2. So substitute the value y bar, which is 1.36, is equal to A1 is nothing but BF into LA and LCC is 3.51 plus 0, the projection is 0, plus 0.3 divided by 2, 0.15, minus we have to find the value of LA and it will be 0.5 times of LA plus 0. BF LA plus LB, area is nothing but breadth into length of the footing required. Cancelled out. LA plus LB, we found this value as 4.16. So 4.16 into 1.36 is equal to 3.51 into LA plus 0.15 LA minus 0.5A LA square. Now this is a quadratic type of equation. Take to the LHS, we get this value. Now on solving, we will get the value of LA as 2.24 meter or 5.08 meter. As this is a quadratic equation, we will get two values, and considering the value of which is 4.16, this value has to be rejected and the value of the eccentric footing is taken as 2.24 meter, nearly taking this value as 2.25 meter. Then the length of the central footing will be, total length is 4.16 minus 2.25, we get the value as 1.91 meter. So the length of the footing B, that is LB, length of the footing B is 1.19 meter. Now the area of footing provided is 1.5, this is BF into length of the footing 2.25 plus 1.91 meter, and this comes as 6.24 meter square. The area required was 6.239 and this is 6.24 meter square. So this is okay. The area has been calculated, the length of the footing has been calculated, and the width of the footing is also considered. Now we will find another value as well. So PV, this is the projection of the B in the longitudinal direction from the face of the column B. So LB by 2 minus BB by 2. So this comes as 0.8 meter. Now the second step is to calculate the net upward swell pressure sigma, and it is nothing but PD by A provided, that is design load by area provided, 1.5 times of PA plus PB divided by 6.24. So this comes as 204.5 kilonewton per meter square. Now remember, this is in terms of the area. Now net upward swell pressure per meter, and this is considered for the longitudinal direction, and for which it has to be multiplied by the dimension in the transverse direction, that is width of the footing. Don't get confused. This is for the per unit meter, that is in this direction. So we have to calculate the swell pressure per unit length per running meter. So we have to multiply by this to ensure that we get the value in terms of the kilonewton per meter, that is UDL. So the 204.5 into 1.5, this comes as 306.8 kilonewton per meter. Now design of footing slab. Firstly we will design the footing slab and then we will design the strap beam. Length of the overhang portion along transverse direction. So as I said, the beam is designed for the longitudinal criteria, that is longitudinal moment, and the slab is designed, or the footing slab is designed for the transverse direction. And if we see the section in the transverse direction, this will be the figure. BF is equal to 1.5 meter considering any of the footing which has greater value of LA, as it is subjected to equal swell pressure. but the value of LA or the projection will determine the moment. Greater the value of projection, greater will be the moment. So length of overhang portion along transverse direction LA is nothing but BF by 2 minus depth of the column by 2, that is BF minus DA by 2. For now, the width of the column, depth of the column is same for both the column, that is 0.3 meter, so it is not a problem to take any of the footing. So LA is equal to 1.5 minus 0.3 divided by 2. So basically this is D. Now this comes as 0.6 meter. Now maximum cantilever moment per meter. As we know, we'll consider this face of the column as a cantilever support and UDL on the projection W kilonewton per meter square here we have, and the length is taken of the projection. Now for the cantilever support or cantilever beam subjected to UDL, the moment is computed as W into L by 2, but this W is UDL, that is kilonewton per meter, but for now it is kilonewton per meter square, so we'll consider per meter, that is unit width. Remember, we will not take this value because this is for the longitudinal direction, but for now we are interested with the transverse direction, so we'll consider for a unit length. So 204.5 into 1 into L by 2, which is basically L square by 2. So 204.5 into 1 into 0.6 square by 2. So this comes as 36.6 kilonewton meter. So this is the maximum bending moment. And from SP16 table C, we know for FE500 the ratio of the MOR and the reinforcement index, which is M by FCK BD square, is equal to 0.133. You can find in the code, and cross multiplying we get BD square FCK into 0.133 is equal to M, and the maximum moment is 36.6. Remember to keep the value of B as 1000 and FCK is 20. We'll get the value of D. So this comes as 117 mm. So this is the depth of the slab required from the bending consideration. Now we have to check the depth from the one-way shear consideration as well. So assuming percentage of steel as 0.15%, shear force at the critical section, that is at distance D. As we know, the one-way shear consideration or the critical section for one-way shear is at distance D, and also understand this point that we will check one-way shear in the transverse direction only, because in the longitudinal direction we have strap beam, so we don't have to design or we don't have to check for one-way shear as well as two-way shear in case of the strap footing, because due to the presence of the strap beam. So considering in the transverse direction the critical distance is at distance D, then Vmax. So for a cantilever beam subjected to UDL, the critical or the shear force at a distance X, or we can say for now D, is nothing but UDL, that is W into length, converting this into kilonewton per meter, into span minus the point of interest, which is D. So we are interested, suppose at a distance D, then the shear force is nothing but W into L minus D, L being the span of the projection or the span of the beam for now. So Vmax 204.54 into 1, converting this into kilonewton per meter, into 0.6 minus D. Now for P% at 0.15 and M20 concrete from IS 456 2000 table 19, you can find or you can interpolate the value of the shear strength of the concrete tau C, and for 0.15% it is directly 0.28 Newton per mm square. You can see in the table. So shear strength, this is in terms of Newton per mm square. So V strength by B into D, converting this into terms of force value. So V strength by B into D is equal to 0.28, and V strength is equal to 0.28 into 1000 into D, considering a unit width. Equating equation 1 and 2, as we have shear strength should be greater than or equal to shear force, that is, or shear strength is 0.28 into 1000 into D is equal to 204.54 into 1 into 0.6 minus D. Now on solving this equation in terms of D, we'll get D is equal to 253 mm and providing overall depth as 325 mm because the value computed from the bending consideration, which was 117, comparatively less, so taking D as 253, so this comes as 325, taking a greater value. So assuming phi as 12 mm bar, now we are computing the effective depth. So assuming 12 mm bar and clear cover of 50 mm, the effective depth will be overall depth minus clear cover minus half of the main bar. So this comes as 269 mm. Now let us compute the reinforcement in the footing slab. So maximum bending moment which we calculated was 36.6 kN meter, and from IS 456 2000 NXG we get a formula for computing the area of steel if we modify that equation, and AST percentage is nothing but 50 is to FCK by Fy into 1 minus under root 1 minus 4.6 bending moment by FCK BD square. So substitute the value of bending moment as 36.6 and B as 1000, D as 269, will get the value as 0.11%. And remember, this steel is to be provided in this direction, that is in transverse direction, because we are calculating the moment in the transverse direction. So the main bar will be in the transverse direction. But we have calculated depth considering P percent as 0.15%. So if we remember, we considered one-way shear, so for which the P percent was 0.15, then we have to at least provide the minimum area of steel as 0.15%. So area of steel required will be 0.15% of BD. And don't get confused, for the minimum steel it will be B into D, but for one-way shear, that is, we have checked the value from table 19 in which the value is computed with respect to B into effective depth, but minimum area of steel is 0.12 into B into gross depth, that is capital D. So many of the YouTube videos are calculating the minimum area of steel with the effective depth. That is not correct. Now provide B as 1000 and D as 269. So this comes as 404 mm square per meter. Please note, we are considering for unit meter. So per meter. Considering phi as 12 mm, then the spacing required will be width of the section divided by area required by area bar. I have discussed about this formula many times, so I'll neglect this for now. So width of the section is 1000 as we have considered, or as we have calculated the area of steel per meter. So the width of the section should be 1000 by area required is 404 divided by bar provided was 12 mm, so pi d square by 4, pi into 12 square by 4. So this value comes as 280 mm, which is a greater value. This type of spacing cannot be provided, although it satisfies the criteria that should be less than 300 mm. So spacing is 150 mm. This is also from IS code. You can number of bars required will be equal to. Now I'll compute the number of bar considering the whole section. So number of bars required. So firstly I'll do for the footing A and then we'll do for the footing B. So as I said, this will be provided in the transverse direction. So the width of the section will be 2250, that is LA, minus 2 into clear cover. We have to provide clear cover on either side. So 2 into 50 by spacing is 150 mm plus 1. So this value gives the number of spaces, and for number of bars we have to do plus 1. So this comes as 16 numbers of bars. So we have to provide 16 number of bar in this particular direction. So provide 16 numbers of 12 mm bar at 150 mm center to center in transverse direction for footing A. Similarly for footing B, the value of LA is LB is 1.91 meter. So if we substitute the value 1910 and remaining terms will be same, so we'll get 13 numbers of 12 mm bar at 150 mm center to center spacing in transverse direction for footing B. Also we have to check for the distribution reinforcement in the footing slab, and considering the nominal reinforcement, AST provided will be 0.12% of BD. So remember, capital D, 0.12 by 100 into B is 1000 mm into 325, which is the overall depth. So considering this value, will get 390 mm square per meter, and assuming phi as 12 mm and spacing, width of the section, area required, area of rebar, So 1000 by 390 divided by pi d square by 4. So this comes as 290 mm. So provide 5 12 mm bar at 150 mm center to center spacing along longitudinal direction. So this is about the reinforcement of the footing slab. So the next step is the design of the strap beam. Basically the strap beam is designed for the longitudinal moment and the shear force, and the width of the beam has to be fixed, and generally the value of the width of the beam is taken as the maximum of the depth of the two columns. So for now the depth of the column is same for the both A and B, so we'll provide width of the beam as 300 mm. Now let us calculate the shear force at the critical section, which we have already done for the combined footing as well. So considering central, that is the force at the center of column A, as design load 496, and at the mid or the center of column B 779.5. so shear force at the outer face of column A, so this is the outer face, this will be the inner face, this will be the inner face, this will be the outer face. So obviously it will be 0 at the outer face of the column A, as there is no force being acting and there is no support, there won't be any reaction at the face of the outer face of the column A, so it will be 0 kilonewton. Shear force at the inner face of the column A, so if we come to this point, now we have force acting, and considering left to right upward positive, okay, we are coming from left to right upward positive, and also we will have swell pressure acting particularly throughout the footing span. Are you getting my point? So this is for footing A and this is for footing B, and the value is, so we have computed for per meter length, which was 306.8 kilonewton per meter. So shear force at the inner face of column A we are considering at this particular point, so 306.8 in, so we will take this much span. Width of the column A is 0.3, so from this point it will be 0.3 minus 1.5 into 331. This is the design load, so which is basically 496. Okay, so this comes as minus 403.55 kilonewton. Got my point? At the outer face of the column we will have minus 403.55 kilonewton. Similarly, shear force at the right edge of the corner footing, so basically this is the right edge of the corner footing D. So if we see here, we are talking about this face, right face. So for this 306.8 into 2.25, now this will be acting for the whole span of the footing A, 2.25. okay, the swell pressure will be acting on complete or the total base, so 2.25 minus 496, so this is nothing but the design load 496, considering this point upward positive, downward negative from left to right, so this comes as 193.5 kilonewton. And shear force at the left edge of the central footing, so now we are considering this particular face, that is the inner face, or we can say left edge of the central footing, or we can say internal footing, which will be same because there is no any external force acting at this particular point, so the shear force will remain constant throughout the section D to E. So if we see this point as D and this point as E, then it will be like there is no any swell pressure acting on the section D to E, hence shear force at the left edge of the central footing E will be 193.5. remember, the strap beam should not be subjected to any swell pressure, that is we will design the strap beam considering that there is no bearing on the strap beam, hence the section D to E there is no any external or extra force acting, hence the shear force remains constant from D to E, and the shear value will be 193.5 kilonewton for point E as well. Shear force at the inner face of the column B. The value of shear at point E is 193.5, so we'll continue, plus 306.8 into half. Now we'll take this projection only. We have already computed this value as 0.8. Again I will show you. 1.91 minus 0.3 divided by 2, so this value comes as 0.8. okay, so we are coming from this direction to this direction, hence, so from this point we will consider only this much of span of the UDL. So 0.8 into 306.8, so this comes as 493.87 kilonewton. Similarly, at the outer face of the column B, 439, so the shear force at this direction is 439 upward, plus 306, so this much distance, 306.8 into 0.3 by 2 minus 779.5, so this value comes as minus 246.35. So now let us understand the shear force from the shear force diagram. So at the outer face of the column, which is point C, we found the value as 0, and at the inner face of the column A, we consider this point as A, and we found this value to be as 404 kilonewton. Okay, 403 point something, so 404 kilonewton. Similarly, at the right edge of the corner footing, we found the value to be as 193.5 kilonewton, and as if there is no any, so you can understand from this concept as well. So as there is no any external load in the span D to E, the shear force will be constant. So for point E as well, we had 193.5, and at the outer face of the column B, the value increased and it was 439.87, and at the outer face of the column B, the value was 246.35 kilonewton. So this is the shear force diagram, and at the edge it will be 0 again, as there is no any reaction. So here you can see that at particular point S there is 0 shear, and 0 shear represents maximum bending moment. Hence we have to calculate the distance of 0 shear. So if we consider this distance as x, that is x distance from the internal face of the column A, then we can compute the value of x in this particular way. So for the distance of point of 0 shear S, consider at the distance x meter from the inner face of the column A, so shear force will be 0 at that particular point, and then to compute the shear force at this particular point, we will use this concept, that is shear force at internal face of column A minus shear force due to UDL up to that distance. Okay, so shear force at inner face of column A minus 306.81 into x, which is basically UDL. Now substitute the value of shear force at the inner face of column A as 404 kilonewton. Remember that value will be positive because we are coming from right to left. So on solving, we will get x as 1.32 meter. And as I have already said, that at point of 0 shear, the moment becomes maximum. So maximum moment occurs at point of 0 shear, considering moment from the left side of S. So now let us compute bending moment from the left side. Summation moment is equal to okay, and it is UDL, so WL square by 2. For UDL, the maximum moment is computed as WL square by 2. So W into L square by 2 minus vertical load from column A into distance. So this whole distance is nothing but 1.32 plus the width of the column A. So 1.32 plus 0.3 divided by 2 into UDL, that is 306.81 minus 496.818 into 1.47, which is 1.32 plus 0.15, that is half of the width of column A. So maximum moment comes as minus 327.73 kilonewton meter. So this is the hogging moment. Don't get confused with the negative or positive value, that is just a representation. We are interested with the value that represents tensile and that represents compression profile. So hogging, for now I am taking hogging as the tension profile and compression profile with the sagging profile. Similarly, sagging moment occurs at the outer face of column B. So if you have seen my video of the combined footing, that is for the slab only, then you can understand the profile of the bending for the footing. So projection this, okay, from the outer face of the column, it undergoes the sagging profile. So that you have to understand. Hence, similar sagging moment at the outer face of column B, it is nothing but WL square by 2 again. So span is 0.8 as I have already computed this value, and the UDL is 306. So into 0.8 into 0.8 square by 2. So this comes as 98.18 kilonewton meter. So this is the maximum sagging moment that occurs for the this footing. The mid portion undergoes tension profile, that is bends upward, and for this it will be a sagging moment. And as we have said that the strap beam should not consider any bearing, that means we cannot use the empirical relations to calculate the bending moment, that either is hogging or sagging, because the sagging or the hogging portion is at the mid span and we cannot consider UDL for the strap beam. As we said, it does not come in contact with the swell and hence we cannot consider bearing for the strap beam. So what we see here is we got a hogging moment as well as we got sagging moment. So that means there is a point of contraflexure, that is the point at which the bending moment changes its sign. So first let us draw the bending moment diagram. So at point of zero shear we got the maximum bending moment, which is 327 kilonewton meter. Similarly, at the outer face of the column B we got sagging moment as 98.18 kilonewton. So here you can see the point of contraflexure is this, and let us assume it to be at a distance x distance from the right edge of the central footing. So from this distance, okay, or this point, let us assume this as x, or we can even assume this value, okay, x. So point of contraflexure lies at a distance x from the point F, and we know for point of contraflexure the moment or the summation of moment will be equal to 0. So summation moment is equal to 0, and considering the moment from the right portion 306.81, so that is basically the UDL. So we are considering UDL up to this portion only. So 306.81 into x square by 2 minus moment due to the column load. So this is from the center of column B. So 779 into x minus 0.96. Basically this is 0.8, and considering from the center of the column, so we have to add this distance as well. So the column load is acting from this point, okay. Then 0.8 plus 0.3 divided by 2, so this comes as 0.96. so basically this is 0.805. so computing or neglecting the round of value, I took this as 0.8, but this is 0.805. so 0.81 plus 0.15 we get 0.96. so x is equal to 1.29 meter. So the distance of point of contraflexure from the right edge of the central footing is 1.26 meter. So shear force at the point of contraflexure is 306.8 into 1.29. so this much span coming from right to left, 306.79 into 1.29 minus vertical load, that is from the column B, 779.49. so shear force at the point of contraflexure is 383.71 kilonewton. When right to left, downward positive, upward negative. So the downward force is 779 and upward force is 336. so this is negative. so this finally comes as 383.71. so this should lie somewhere here, okay. so this is point of contraflexure and the shear force is 383.71. so we have computed the moment and the shear force. Now we will design the strap beam considering those values. And before that, we have to understand that if we see the plan of the strap beam, considering this as C point, this as D, and this as E, this as F. For DE portion, we don't see any slab, only there is beam. Hence the beam will be a rectangular type, that is rectangular section is only available. But for the portion C to D and E to F, there is availability of the slab as well, that is beam and slab. Hence we can assume that it can act as a T-beam. So basically T-beam means a flange and a wave casted monolithically. So this is the 3D view. So I'm just making up to half portion, that is I'm neglecting the other footing. So if we see this portion only, this is the beam, strap beam, and this is the slab of the footing. And for CD portion, we have depth of beam greater than footing slab. This is a general condition. We will have the depth of the beam greater than the footing slab. Hence T-beam action is available for this section, considering this as the flange and this as the wave. Hence the depth of the beam is calculated with respect to moment along section where rectangular section of the beam is available. Basically with the flange and the wave, the performance of the beam increases. Hence we will design or will consider the depth of the beam considering the rectangular section only. Hence it will be much more safe. So that means we have to design the depth of the depth of the strap beam considering the critical section, which will be point D, because up to point D we will have a T-beam section and beyond that we will have a rectangular section. And considering the moment diagram, the maximum moment occurs at point S, that is point of contraflexure, and which was at a distance 1.32 from the face of the column, but it lies within the T-beam section. Hence we have to design for the section or for the moment at the critical section, which is basically particular point T, because beyond that the moment will decrease, and the maximum moment that occurs for the rectangular section is at point D. Hence we will design considering point D. So hogging moment at D, MD is equal to this value, which is 306.7, considering 306.81 into 2.25 into 2.25. okay, we are considering this value, moment D. So 306.67 into D, that is for point D it will be 2.25, that is this length of the footing LA into LA by 2, that is WL square by 2 for UDL with the cantilever section, minus 496, that is the design load. So this is 2.25, this is 0.3, so this much distance will be 1.95, so that is almost 2, so minus 266.7 kilonewton meter, that is the maximum hogging moment at point D, so 266. Now we'll design for this moment, and from SP16 for FE500 we have this value for ME by FCK BD square 0.133, D is equal to under root 0.133 into 20 into 300 cross multiply divided by 266.7 into 10 to the power 6 inverse. Don't get confused, I've just placed the inverse sign, that means moment will be upward and this will be the denominator. So this comes as 578 mm. So from the bending consideration we found the depth of the strap beam as 578 mm. So now from shear consideration, maximum shear force, if we see the shear force diagram, at the face of the column B we got the value of maximum shear as 439.87, hence the maximum shear force is 439.9 kilonewton, and nominal shear stress, this is also from code you can find VB by B into D, 439.9 into 1000, converting this into Newton. Width of the beam was taken as 300 and D is to be calculated. And similarly for M20 concrete, design shear stress tau C max is 2.8 Newton per mm square. So this is from table 20 of IS 456 2000. So here you can see maximum shear stress tau C max for M20 concrete it is 2.8. So 2.8, and we know design shear stress should be greater than shear stress, like that is the shear force or shear stress acting on the section, and it is 2.8, 439.9 into 1000 divided by 300 into D, so this value comes as 524 mm, but the value from the bending consideration was 578 mm. So what we understand is that the beam is a flexural element, so we have to design, or the depth from the bending consideration will come greater than that of the shear consideration. So D is equal to 524 mm, and providing overall depth greater of these two values from the bending consideration and as well as one-way shear consideration. So D is taken as 650 mm and providing effective cover D dash as 50 mm. So this comes as 600 mm, which is greater than that of the value computed from bending consideration as well as from the one-way shear or shear consideration. Since there is T-beam portion available, so we have to calculate the effective width of the flange, and from IS 456 2000 page 37 we have for isolated beams the effective flange width shall be with T-beam BF is equal to L0 by B plus 4 plus BW. So L0 is nothing but distance between point of contraflexure. So if we see the force bending moment diagram, this is the point of contraflexure. Now we have to compute the center to center distance between the point of contraflexure, and that is, okay, if we see here LCC, so center to center distance between column, plus BA by 2, so we come to the, that is half of the column A plus half of the column B plus PB. So we are computing this particular distance total minus Y dash. This minus this will give the center to center distance between point of contraflexure. So this is 3.327, converting this into mm, 3327 mm. Similarly B, actual width of the flange, which is 1500 mm, because we have considered the width of the slab as 1500 mm, so the actual width will be 1500 mm. So here you can also see this is 1.5 meter. B, actual width of the wave we have considered as 300 mm, so this is the wave portion, so 300 mm. And DF, depth of the flange, we have considered the depth of the slab as 325 mm. So now let us compute the effective width of the flange. So this portion will be the effective width of the flange. So substitute the value L0 and B plus BW, we get this value as 839 mm. So this is the effective width of flange. So since T-beam action is available at CD, so I have already shown this portion CD, and considering XU is equal to DF, this is the approach for the T-beam design. I have given a link in the description where I have discussed about T-beam. You can see that considering MU is equal to DF, MOR, this can be computed as 0.36 into FCK into BF into DF into D minus 0.42 XU. As we have substituted the value of XU as DF, we can compute, or we can substitute the value of XU as DF here as well. So substituting FCK as 20, BF as 839, DF as 325, D as 600 and XU as DF, which is 325, we get this value as 906 kilonewton meter. And the maximum moment computed, you can see in the shear force diagram, 327. So the MOR is greater than MX, so the neutral axis falls inside the flange. Okay, this is the neutral axis, falls inside the flange, that is XU is less than DF. Are you getting my point? XU is less than DF, hence compression occurs in the flange section. So the flange section is considered for the compression only, and the wave is considered for the tension. Now we'll calculate the longitudinal reinforcement in the beam. So for longitudinal reinforcement beam, or for longitudinal reinforcement at top, considering maximum hugging moment, so this will be the orientation of T-beam, and the reinforcement at the top is subjected to the tension, it is provided for the tension. And for longitudinal reinforcement at top, we will consider the maximum hugging moment because due to the tension, and which was 327.7 kilonewton meter. Remember, we calculated the depth considering the maximum moment at the critical section, which was the D, because only rectangular section is available at that particular point. But for calculating the reinforcement, we are taking the maximum bending moment, which occurs at point of zero shear. So we have AST 0.5 FCK by Fy into 1 minus under root 1 minus 4.6 FCK BFD square into BF. This is the point we have to understand. The maximum moment occurs at the T-beam section, and we are considering the effective width. So this is why we calculated the effective width of the flange. So we'll use the depth, we will use the width related to that point, that is the width at which, or the section at which the moment is occurring. So the maximum moment occurred within the flange or within the T-beam section, we are using BF. So substitute the value M as 327 and BF as 835. With depth of the beam as 600. Also you have to understand that if we see, this is the tension reinforcement, and the effective depth is different for the tension region and for the compression. But for now I am taking same for tension as well as compression, because it is a different process to compute the effective depth for the tension region, because we have to consider the center of gravity of the reinforcement. That will be a different process. I will show you in the other video, but for now I'm taking same effective cover for tension reinforcement as well as the compression reinforcement. So substituting value, we get area of steel as 1347 mm square. So minimum area of steel is 0.12% of BFD. Don't get confused, I'm taking BFD. So this comes as 652 mm square. Flexural reinforcement 0.85. So this is a different thing here. You can see for flexural element we have to consider minimum flexural reinforcement, and you can find this in the code page 46 IS 456-2000 clause 26.5.1.1. minimum tension reinforcement shall not be less than AS by BD is equal to 0.85 FY. So if you cross multiply, we'll get this term 0.85 by FY into BF into D. So we are considering the flange section, so 855.78 mm square. Considering section at point D, which consists of a rectangular section only, so we'll compute the area of steel with that moment. So at D we had 266.7. so area of steel is equal to same formula, but the value of B will be BW here, that is only web. So it is 300 mm. So substitute the value of BW as 300 mm, we'll get 1234 mm square, which is less than that of the value computed for web T-beam. So provide area of steel required maximum of this 4 value 1347 mm square. So if we check minimum area of steel and flexural reinforcement with BW, it will come less than these two values, so we will not compute that. So just comparing this value, we will get the area of steel required, so 1347 mm square. Now let us calculate the number of longitudinal bar required then. Assuming phi as 20 mm, number of longitudinal bar required will be area of steel required by area of individual rebar. So area of steel required was 1346 mm, and for the area of the individual rebar, pi d square by 4, pi into 20 square by 4. So this comes as 4.3, nearly taking this value as 5 number of steels, that is 5 NOS. Area of steel provided will be 5 into area of individual rebar, pi d square by 4. So this comes as 1571 mm square, which is greater than that of the area of steel required. So for tension reinforcement, this is the point we have to understand. For tension reinforcement, the diameter of the bar should be selected or should be restricted such that the value of M1 by V plus L0 does not exceed the development length. So M1, this is the moment of this moment of resistance of the section considered. So the value is computed with this formula 0.87 Fy AST into D minus 0.42 XU, where XU is 0.87 Fy AST my 0.6 FCK BF. So this is from the IS 456 Annex G. So we are considering the maximum steel for the T-beam section, so BF. Now substitute the value, we'll get the value of XU, and then the value of XU is computed or replaced here, and substituting area of steel, remember area of steel is 1571, D is 600, we'll get M1 as 377.37 kilonewton meter. Similarly V, this is the shear force at the point of contraflexure, so this comes as 383.7 as we have already computed this. Similarly L0, this is 12 phi or D, whichever is greater. So maximum of these two values taken, and 12 into 20 240, and D which is 600, so we'll take L0 as 600 mm. Similarly LD, phi sigma s by 4 into tau Vd. Phi is the bar size, that is 20, sigma s is the design stress, so 0.87 into 500, that is sigma s is equal to 0.87 Fy. So you can substitute the value of Fy. 4 into tau Vd, this is design bond stress, which is 1.2 for M20 concrete, and it should be increased by 60% if deformed bar is used. Generally we use deformed bars, so 1.6, and this comes as 971 mm. Now substitute the value of M1, V and L0 in this equation, converting this into Newton mm, in this converting into Newton as this value is in terms of mm. So this comes as 1583 mm, and this is greater than LD, hence the bar provided is safe, that is okay. Similarly longitudinal reinforcement at bottom, considering the maximum sagging moment. So this has to be computed with respect to the maximum sagging moment, which was 98.1 kilonewton, which occurred at the face of the column B. And now effective depth for compression zone, as I have already discussed that we have to consider different value of effective depth for compression zone as well as the tension zone. But for now I am taking equal value, because for computing the effective depth of the tension zone it will be a different process. I will make a short video about that in the next video, but for now I am taking equal effective depths just to make you remind of this point. 600 mm AST required. Now substitute the value for maximum sagging moment which occurred. We will take BW, and D square we can just take this value, M which is 98.1, D will be 600, so this comes as 409 mm square. Minimum area of steel 0.12% of BWD, so substitute the value and we will get 234 mm square. Minimum flexural reinforcement 0.85 by Fy into B into D, so this comes as 306 mm square. Area of steel required 409 mm square, that is maximum of these values. Now assuming phi as 12 mm, number of bars required will be 409 by 113, considering 12 mm the area of steel will be 113, then it comes as 3.6 and the value is nearly equal to 4 NOS. So area of steel provided will be 400 into 113, so this is 452 mm square. So the now design of the vertical reinforcement in beam. So shear force at the critical section Vmax by BD, and converting this into Newton, 439 maximum shear force is 439.87, which occurs at the face of the column B. So this is the critical section into 1000 by 300 into 600. So this comes as 2.45 Newton per mm square. Similarly, percent of tensile steel provided is area of steel provided by B into D. So area of steel provided is 1571 divided by 300 into 600 into 100%. So this comes as 0.86%, and for Fe 500 and P percent as 0.85%. From IS 456 2000, tau C is equal to 0.59 Newton per mm square. Since tau V is greater than, that is the nominal shear stress is greater than the design shear strength, hence shear reinforcement is necessary. And then how much shear reinforcement will be necessary, that will depend on the excess shear force than that of the design shear strength of the concrete. Shear strength of concrete is equal to 0.59 into B into D by 1000 square, that is design shear stress into area of the effective area of the section. So this comes as 107 kilonewton. At the inner face of column A, support is, so maximum shear force at the vicinity, at the face we computed 404. So design shear force will be shear force, maximum shear force minus design shear strength of the concrete, VC. So this comes as 298.56. so the reinforcement has to be designed for this much force. Providing 2 leg 10 mm stirrups, area of stirrup will be 2 into this is number of leg pi d square by 4, this is the area of the section, 2 into pi d square by 4, 157.08 mm square. So I have provided a link of the video in which I have discussed about the design of beam in shear, so you can understand all these terms. So for now I am just going through surfacely. So ASB is equal to 157.08 mm square. From IS 456 2000, spacing required will be, so this is from IS code, you can see that 0.87 Fy ASV into D by VUS. So substitute the value, ASV as 157.08, effective depth is 600, and the shear strength or shear force for which we are designing the stirrups or the vertical reinforcement is 298.56. So this comes as 138.6 mm, and generally the value is kept in terms of 25, so providing 10 mm 2 leg stirrups at 100 mm spacing, or we can provide at 125 mm. So taking 125 mm center to center spacing at point inner face of the column B. So the shear force at the inner face of the column B is 439.87. So maximum shear force, that is 439. Design shear force will be Vmax by Vc, that is the shear strength of concrete. This comes as 332.8 kilonewton. Size of the stirrups 10 mm. The ASB and SB will be same. ASB will be same. For SB, substitute the value of VUS as 332.8 kilonewton, and other things will remain same. And this comes as 122.6, keeping in terms of 125, that is multiples of 25, providing 100 mm. Let us check that up to which distance this much vertical reinforcement is provided or is needed. So assuming that at a distance x from the face of the column B, then at a distance x, if we consider, then we have this value as well. Okay, so this is 306. So shear force 439.87 minus 107.992, because up to this value there is no shear reinforcement is necessary. Beyond this value only we will require shear reinforcement, and considering this much design force, that is maximum shear force, we can compute this value. So this comes as 306.81 into x, so that is the reaction due to the swell pressure. So this comes as 1.1 meter from the inner face of the column B. Okay, you can do this for column A as well. That will be 403.55 minus 107.992 divided by 306.81, and that value will come up to which the shear reinforcement has to be provided of that spacing. Similarly, at the outer face of column B, which is the projection, Vmax is 246.35, VUS will be 246.3 minus 109 and 107, sorry. So this comes as 1384.6 kilonewton, and spacing required will be 0.87 Fy by ASB into D divided by VUS. So this comes as 291.3 mm, providing 2 leg 10 mm stirrups at 150 mm center to center spacing. Similarly, at point D, from point D and E it will be, so 193.5, VUS is 87.3, that is 193.5 minus 107, so this comes as 87.3. Substitute the value and then we'll get 469.6 mm. So we'll provide 2 leg 10 mm stirrups at 150 mm center to center spacing, but according to the code the value is 300 mm, maximum spacing is 300 mm, but considering the municipal rule it is provided 150 mm center to center. So this is how the shear reinforcement and the longitudinal reinforcement is designed for the beam. So this is the reinforcement detailing. So we computed 12 mm bar, 150 mm center to center spacing in transverse direction for footing. So you can see here, these are the transverse rebar, that is the main rebar, 12 mm, 150 mm center to center spacing. Similarly, the distribution reinforcement was computed 12 mm bar at 150 mm center to center in the longitudinal direction. So 12 mm bar, 150 mm center to center spacing, which is the distribution bar in the longitudinal direction. Similarly, in the transverse direction we have 12 mm bar at 150 mm center to center spacing as the main bar. 325 mm is the depth of the footing slab. Similarly, for beam we had computed 4 numbers of 12 mm bar at the bottom, and at the top we computed 5 numbers of 20 mm bar, providing in 2 layers. Similarly, from the face of the column A we provided 10 mm 2 leg stirrups at 125 mm center to center, and this will be continued up to point D. Okay, up to this point we'll provide 10 mm 2 leg stirrups. So this is the footing, hidden line is representing the footing. Similarly, from the face of the column B, that is the inner face of the column B, up to point E, will provide 10 mm 2 leg stirrups at 100 mm center to center spacing, and for the outer face of the column B we provided 10 mm 2 leg stirrups at 150 mm center to center spacing, and at the mid span, that is from point D to E, we provided 10 mm two leg stirrups at 150 mm center to center spacing, and the depth of the beam is provided as 650 mm. And while providing reinforcement in number of layer, we have to provide spacing, so providing 20 mm spacing in between them, and the area of steel. So this is the tension reinforcement, and the effective depth is computed considering the center of gravity of this area of steel. So it will be a different case that we'll talk in the next video. So this is the L section, cross section at XX, and the plan of the strap footing. I hope it helped you. Do like and subscribe. Thank you.